Thank you, and I want to thank the organizer for inviting me. This is work that I have the pleasure to do with colleagues at RIKEN, with Florence Tama and Osamu Miyashita. And it is also part of the joint laboratory for extreme scale computing, JLESC, and we will have a meeting in April here, so I'm looking forward. So Analytics4NN, or Analytic for Neural Network, is a project that is looking for designing efficient workflow to reduce the time and resources that we need for generating neural network architectures. And here you have the fantastic collaborator, student, postdoctoral researcher, and our collaborator at RIKEN who are joining us in this mission. So I want to start with data, and I join Satoshi in saying that our mission as computer scientists and high-performance computing expert is to enable science. And in my case, we want to enable science through the analysis of large data sets. Here you have a couple of examples. Behind each of these data sets, we have exciting scientific discovery that can change our lives and the society. But we are not looking at in general data, we are looking at a specific type of data that we are receiving from our colleague at RIKEN. It's data that come from X-ray free electron laser. And in this picture, you have a little bit the story of this data. They are the two-dimensional protein diffractions patterns that we collect through this mechanism. And what we want to do is, given the two-dimensional pattern, we want to support Osamu and Florence to get an understanding of the configuration of the proteins that are generating this two-dimensional pattern from the three-dimensional point of view, from their features. So the part that we have to understand is that these kind of images are very rich in information about the three-dimensional part of the protein. However, as you see here, this kind of picture are not easy to read from the point of view of the human being. And what is that we want to identify? This is an example of information we want to capture, which is the conformational structure of the protein. So we can have different protein, and we want to understand what is their three-dimensional shape. And that comes also with some challenges because we are not letting the protein falling in front of this laser in a specific configuration with specific angle. There is a lot of randomness in the way in which the protein is indeed transformed into a pattern. So here in this case, you have two different proteins that generate two different type of patterns. And what we need to identify is which pattern is which configuration. Now, not everything is easy, especially because when we look at experimental facility, we have to keep in mind that the images we capture come with noise. And so here we have example of different type of images that have a different type of intensity of the beam. And that consequence is that the knowledge embedded in the image is also harder to identify. And we use this type of artifact, which is the intensity of the beam, as a proxy for the possible noise that experimental data can have. So now, with these images, the most natural thought is, why don't I use neural network to identify this feature? And indeed, it's a great approach. But we have also to consider that extracting information from these images means building what it is, a customized neural network that is customized for the type of data set we have. And the training of this neural network is quite expensive. So let's look for solution, and we can look definitely at Neural Architecture Search, or NSA. NA is NAS. And in this context, we have many NAS that we can use to accelerate the search of these neural network models. Now, there are a lot of studies that are quite recent also that look at the limits of NAS. And so here, this is an example of such studies. Is from a different group. But we agree fully with the limitation of NAS that this paper is pointing out. The first limitation is that if we look at NAS as they are today, especially the ones that are classified as black box techniques for the search of neural network models, they are a monolithic couple process in which you have that both the search strategy and the performance estimate strategy are connected, coupled. And so that means that we have also a reduced potential for optimizations. A second challenge that we have to face when we use NAS for the training is that there is an amount of time that results in an amount of energy for the training of our models. And so that comes with the fact that we have to consider the fact that we have a limited amount of resources for our training. And to support that claim, I want to show you another image that comes from another paper from colleagues who did some work to look at the aspect of flops for major milestone in AI and in machine learning system. And you see that there is some sort of linear flops until we get to the point of deep learning and large-scale models. And here we have an explosion in terms of number of flops that are required for this training, which result also then in an amount of energy that we need to invest. Last but not least, and it's probably the part that it's for me the part that I'm more passionate about is that there is this aspect of obscure process for the generation of our neural network models. And that is something that results in not being able to explain why we have specific model, what is the rationale behind that model being the most accurate in our search. So what we propose is a workflow that we call Analytics4NN, and that has specific features. And I want to take you through the properties of this workflow in the context of the data set that I introduced at the beginning of my talk. So we will see how, in our workflow, we want to transform the NAS implementation from a monolithic software tool into a modular workflow that is more prone for optimization. And that is through generation of adaptable neural network fitness prediction. It is about building an open access of neural network data. And in this context, once we have built this workflow, I will show you what are the results when we use this workflow in the context of the data set I was introducing to you, the two-dimensional images from experimental facility. So let's start from the first approach of decoupling the two strategies of search and performance evaluation. And so in that context, we start with our images, our input. And from this set of data, we want indeed to analyze the conformations that are embedded. Now, we are using in this context simulated data. We are not using experimental data yet, but that will be our next challenge. And of course, we use NAS. We are not discharging or saying NAS are not good. We are still using NAS, but we want to augment them. And so when we use NAS, we have plenty of choices. These are black box techniques. You see here we had started looking at which NAS are available, what type of search they are leading, and are they open source? Because we want to augment them and so plug in our workflow. And so in this study, we use one specific NAS, which is an evolutionary NAS. And in this context, we augment the NAS with what we called a prediction engine that allow us not only to develop a parametrical model for the evolution of a model, but also to return to the NAS information about whether we can terminate the training. So, and I will tell you a little bit more about this approach. Now, in the context of explaining what is going on inside the training, we are committed in our workflow to capture the model as it evolves from epoch to epoch and save that information into what we call a neural network commons, which means it's not just the architecture, but we want to save all those metadata that allow us to analyze and reason about why a model is better than another. So I want to focus into the generation of these, what we call adaptable neural network fitness predictions, and tell you a little bit more how we are addressing that challenge. So it's a component of our workflow that has two major steps. First of all, it has an input, which is what we call a partial train net model with its performance, and we pass this information, this partially trained neural network, into our prediction engine, in which we apply what we call a parametrical modeling of the learning curve. And the second step is about the prediction analysis, in which we try to extrapolate the final accuracy of that partially trained neural network before that training is indeed completed, and then provide feedback back to the NAS if it is the time to terminate that. And so we have this composable implementation in which a user can plug into our engine different type of models that can model not only accuracy but also losses. And in this case, we have a specific example that is passed, and we build through a loop between the parametric modeling and the prediction analyzer a function that look a little bit like this one. So these are two, oops, there is some delay in the slide, yeah. These are two examples of neural network models that are in training. And here you can see that we pass to our engine some, every half epoch, the architecture, and at the for in this case on your left, after 4 epochs, our engine has already identified the function and projected what would be the final accuracy. So we can go back to our NAS and inform the NAS that it is worth to terminate that, because we know what will be the final accuracy, or we project what will be the final accuracy of the model in question. So on the left, you have a model that is learning, but we can also cover models that, for example, on the right, you have a model that is never learning. So by doing that, what we have is that we can terminate the training before the training is completed. We can generate, in this case, more a broader search in which we are looking into reusing those resources that otherwise would have been used for the complete termination of the training. And in that case, we end up saving time and resources for a better search. Now, when we have this process, iterative process of searching for the prediction, searching for a parametrical function that predict the neural network model accuracy. What we do at the same time is saving the architecture, the model, not only from the point of view of its structure, but also the weights and other information, because we want indeed to understand and reason about why one model may be better than another. And so there are an aspect of this workflow that is also the visualization. Visualization, in this case, of similarities. And so we start with our neural network architecture. We represent it through graphs and binary arrays. And then with that in mind, we can then look at subsequences of these models and look for matches. So in this case, for example, you see that we are looking at subsequences of different length, and they can go, it's a small model, this one, so it's it's for convenience, for visualization, but we have subsequences of different lengths that go from 4 to more than 20 components, and then we are looking at the accuracy of this model and their frequency. So there is 3 different informations. So in this case, for example, we see that we have this interesting approach in which, as we are training this model, we have a formation of what look like a horseshoes, in which we have specific models that are going through a very high accuracy and have some subsequences that repeat themselves, and another group of models that are diverging and are going through the other direction in terms of accuracy. And what we can do in this case is zoom in into group of this model and visualize, like in this case you have in your right, we can visualize the networks and compare them, so to identify the repetition in subsequences of models that are more successful or are less successful, adding an aspect of explainability to why a model is better than another. So we do believe in sharing data and sharing software. So open access for data is important. And so the work we have been doing with Analytics4NN, we are uploading all the frames that we are, all the models and their evolution from epoch to epoch into Dataverse, so that people can have access and can also look at aspect of why a model is better than another, as we think it's an important aspect for our understanding and explainability of neural networks. So let's go back to the initial problem, which is, okay, now we have built this workflow. It has addressed some of the challenges that I pointed out at the beginning of my talk. So can we use it? And are we indeed gaining time and resources while preserving the accuracy we want to achieve in the process of identifying the protein structure? So we are considering our workflow. We are looking into metrics like accuracy, and so the higher the better. We want to maximize that. And flops, and in this case, it looks something very non-HPC. The lower, the better, so the less flop we do, the better. And then, of course, as scientists, we are not really speaking in terms of flops, but we are speaking in terms of work clock time. We want to minimize the time that they are waiting for. We go back to the principle of having different data sets with different level of noise, which means that we look at 3 different classes of data set with different bin intensity, and so more or less challenging to identify the embedded knowledge. So we use a train split that is 80-60, and we have something like 80,000 images for each of these 3 bin intensity. So let's look at a couple of results. And first of all, aspect of accuracy and flops. So we are representing here two different sets of data, one with using the NAS without our augmented workflow, and it's on your left. On your right, you have the NAS that has been augmented with Analytics4NN. So how do we read this image? We have three types of symbols with three different colors for the three different beam intensity. What we want is that for the flops, is the lower the better, and for the accuracy, of course, the higher the better. And so here it was not really whether we can do better, but whether we can do similarly to the NAS when we truncate the training in advance. So the NAS was set so that it was executing 20 epochs for each of the model. In the case of Analytics4NN, we were cutting that earlier because of our parametrical models. And so when we compare this, we see that, for example, when we have high-intensity beam, which is the sort of idealistic situation that we don't have, of a clean data set, very well marked. So we see that, okay, the NAS is doing fantastic, but it's not really the reality of experimental data. And so when we go to a condition in which we have a medium beam, which is still with noise injected, we see that the Analytics4NN is able to outperform the NAS. And what happens also is that we are substantially cutting down the time for results. So here it is again the three data set with the three different beams intensity. And the nice part of our workflow is that it has a component of parallelization, of analysis of our models that is, and I don't want to say the word, but embarrassing parallel, but there is nothing to be embarrassed. The point is that if we have GPU, we can distribute the aspect of modeling the prediction across different GPU, as it happens here. And so we dramatically cut down the time for our for reaching the same conclusions by using the GPU on the nodes. In this case, we had 4 GPU, but it's almost linear because we can indeed distribute the models and the prediction. So what about other methods? Before to move to use neural network, we were looking at approaches that were based on traditional machine learning and autoencoders. And so here you have a comparison with a method that is XPSI that was developed before. And we see that with Analytics4NN, we match the accuracy. Sometimes we do even better. And the time, of course, is going down because we can also leverage aspect of concurrency and parallelism on the node. So I've been running a lot, and perhaps some of you may have sort of said, oh my goodness, it's too many slides, too many pictures. But let me go to the end of this talk with some lesson learned and some time also for question. The first one is that strategy for successful optimization of neural network training are needed. And that aspects that are important in this strategy are decoupling the search and the estimation strategy, minimizing the energy consumption, and as I told you, for me, very important, providing some explainability of our work. What did you see here? Well, we presented an example of workflow that indeed is developed and designed, driven by these three, oops. Well, the last slides I had was a little bit a summary of what we were able to achieve with our workflow for this specific use case. And the fact that everything, the software and the data are available to the point that we presented this work at ICPP and we submitted that to the ACM digital library, and we got badges that prove the reproducibility and replicability of our work through open access approach for data and for the code. And I think that there was a nice QR code for assessing that. If we are not able to go back, just come find me. I'm here for the entire. I'm actually on the next the panel at the end of the day, so I will be pleased to give you the link to software and data or share with you any material that you may be interested in learning. And so I think that we can stop here and we can perhaps have questions.
Thank you, Michela.